Hello everyone and welcome to the HSC equilibrium calculations tutorial. In this tutorial we will go through the basic settings and also use of the equilibrium calculations module with few examples. First, let's go through the main window. So here on the left we have the Excel sheet where we write the definition of our system with phases and species. And on the right side, we have some calculation options and parameters where we set the system state and independent variables for the equilibrium calculations. Up here, we have some basic menus and also some shortcut buttons, such as creating empty file or creating empty file with the database or adding phase to the spreadsheet. Most of these things can also be done by right-clicking on the spreadsheet. You can see that there are a lot of menus here, and also you can browse database through here and search your species for your system through here. So let's start with a simple example where we study the formation of ammonia gas in the presence of nitrogen and hydrogen when we change the temperature and pressure. So I write the species here, and as you can see the equilibrium module gives or predicts the species that you are writing there. So if I write now ammonia gas, it will suggest me these kind of species, and I can select what I want with the arrows and enter. Okay, so now I have defined all the possible species. I rename my phase. Okay. And now I have all the required species for my system. I define some initial amounts here. Okay. And that's it. Now I have defined the possible species and the initial amounts. So next we define the calculation options and also the system state and independent variables for our system. So if we start up here, we have the calculation mode, and by default this is set as normal, and in most cases this is the correct choice. So there are some other calculation modes here, but we don't go through them in this tutorial. If you want to check them, you can use the help here. Then we have the step mode, which is important if you want to add some species during the calculations or remove some species during the calculations from the system. And if I check what we have here, we have either we have two add amounts, so either you add some set amount each step, or you say what is the final amount, and then the program will calculate how much needs to be added each step. And then we have these remove options here. If you want to remove some particular species or phase from the system, you can use these options. And again, rest of these are more advanced features that if you want to look into them, you can check from the help. We also have these allowed iterations here, and if we want to do the iteration calculations, we can select it, but in this case we don't need it. Then we have the user-defined parameters, where we say which of these parameters we want to set for the system. So in this case, when we want to study the temperature and pressure, we select this NTP. Then we select the number of independent variables, and we have the option of selecting 0, 1 or 2. If we select 0, then that means that we cannot define the state change for any of these. We just define one single state for the system, and then when we calculate and we press this show chart, it shows us the result of that single point what we set. So we said that the temperature is 25, pressure is 1, and we get the results here. Okay. So next, let's try to set the number of independent variables to 1, and let's change the temperature from 25 to final state of 1000. Here we say how many steps we want to have between that, so I'll select 51. The pressure I set to 1 bar, and then I calculate and show chart. Now it gives me this kind of a dialog where I select what I want to see in the chart. So in the x-axis I want to see the temperature, yes, and then I want to see the equilibrium amounts in the y-axis. So I press finish and I get this kind of image. So now I can see that when I change the temperature, then the system will change according to the thermodynamical equilibrium. The system will change like this. And here I can filter out different species from the system, or I can just select some particular phases here. Now we only have one phase, so I can only select that one. I can also filter out with elements here. And as for the chart, I can zoom in, zoom out, or I can change the axis here by dragging this dot over here, or I can just click on the chart and then move around. And also there is this menu button over here where I can get more options for my chart. So I can refresh here if I somehow distort the image or zoom outside of any known range, then I can easily here refresh the chart. I can copy the chart, and also there is this format chart menu where there is a lot of options for the chart. So there is the general options, then for the axis, legend box, for the line series, and so on. So you can customize your chart with these menus as you like. Okay, so now I go back here and then I close this. Okay. Now at this point, let's check one very important thing regarding the equilibrium calculations. So as we in the beginning we set the phase and the species for the system, but we also have the phase type over here. And if I click it, I can get this drop down here where I can select the phase type for my system. And it is very important to know which type your system is, or the phase. So for example, in this case I have the gas phase where everything is mixed, so I use the mixture phase. But for example, for solid phase, often you might want to use the pure type. So if just for example we check how does the chart look with the same system state, and we compare it to the previous one, we can see that we get very different chart here. So we get sudden changes here after before 200 degrees of Celsius. So the chart looks very different, and it means that the results are very different. So it's very important to always remember to check this phase type so that for each phase it is correct. And usually mixture, pure, or aqua is used. This aqua is for the water phase, and it uses these picture parameters and calculations to estimate the activity coefficients of different ions in the system, and it is used for the water phase only. As for these are for binary systems, which we don't go through here. If we want to take a closer look how they are done, then you can check again the help file. But the most important thing is to remember that mixture pure and aqua, those are the most relevant ones. Okay, next let's see how the system behaves if we change the pressure and the temperature at the same time. So to do that, we need to set two independent variables for the system, and then check the pressure as the other one, and then set the initial and final amounts, and then in how many steps we want to calculate it. And then we calculate, and as you can see, it takes a little bit longer time now, since there are many more points to calculate for each step of temperature. It needs to go through each step of pressure. So now I press show chart, and for the axis I select temperature and pressure for the Z, and for the Y I select the equilibrium amount again, press finish, and now I get this 3D image of the system in the function of both pressure and temperature. And if we study the image, we can see that okay, clearly the temperature effects, but also the pressure effects. So we have these slopes for the different species that we can check from there. And you can sometimes see pretty interesting results with this 3D diagram. Okay, and now we can go back. We can also select some other variable here. So for example, we can check how the volume behaves, and for that we get this kind of image. So here we don't have the species separately, we just have one volume here. Okay, this might look better in 2D chart, but anyway, you can test out yourself how they look, each of these variables here. But for this system, I think we are fine. Then if we check some of these other options here, so here we have the phase data over here, and it's basically the same thing as this phase type what we have here. Also we have some calculation options, so we can leave out the mixing entropy or check the Chris-Koppel. I won't go through these. If you want to check what they do exactly, then you can again check either the tooltip or the help files. Then as for the final option here, we have the target calculations. So this is actually can be pretty handy. So if I select now one independent variable, and then I check it as temperature, and I want to, let's say I want to study in which point exactly I have 1 kilomoles of ammonia gas. So I can set the target calculations here, and then I can calculate, and the program will calculate the results here and tell me what is the system that fills the requirements of my target calculations. So in some cases this can be pretty handy, but if I set some impossible amount there, then the program will tell me that okay, cannot find the solution. But if I try to find some sensible state for the system, then it finds it pretty quickly. Okay. Also, we have this results sheet here. So after you have pressed calculations for the first time, then you get this results sheet here. If you want to copy your the results to Excel and draw your own graphs there, then you can use this data over here. Okay, let's move on to the next example. So I press this empty file over here to get empty sheet, and then let's see how does the aqua phase type work. So I write the system here, and let's study how the, for example, how the sulfuric acid dissolves in the water and how the ions behave there. So I write the species of the sulfuric acid. Okay, and then here, and then I insert a separate phase for the sulfuric acid. Okay, and now because I have a water phase over here, I write aqua there, and then I set the phase type as aqua. So now you can see that the activity coefficients are grayed out, so the user cannot change them now because the program will estimate these the activity coefficients of all these species in the system now. And as for here, well, it doesn't matter. I can change it to pure because there is only one species. It doesn't really matter what phase type I have there. Okay, so let's say that we add some sulfuric acid and we want to study how the ions behave or how it dissolves into the system. So we check the NTP, and then we want to have the step mode as add amount, yes, and the independent variable should be the X amount. So this lets us write a value here. So now we are adding 0.1 kilomoles of sulfuric acid each calculation step, and I will say that the initial amount of water is 50 kilomoles, and we can calculate 51 and in temperature of 25. Okay, let's calculate and then see the results. Amount and equilibrium amount, that sounds good. Okay, we get this kind of image. If we filter out the water, then we can see more clearly how the amount of ions behave in the system. Okay, so there is quite good dissolution in the system. If I want to now study how the program actually changes the activity coefficients of my species there, I can select this one and draw the chart, and I can see that how the estimation actually changes the activity coefficients in the function of added sulfuric acid. Okay, then finally I can also check the pH of the system, and I can see that the more we add the sulfuric acid, the lower pH we get, which makes sense in this case. Okay. When using the aqua phase type, the activity coefficients are iterated in iteration rounds. And down here in the phase data, you can see how many iteration rounds the program will calculate after each step. Usually the default 3 is enough, but sometimes if you want the calculations to be more exact, you might want to change this, for example, to 5 and then calculate again. The calculation time increases a little bit, but often it is still quite fast. So that's it for the water example. Finally, let's check one more example where we study how the system behaves in copper smelting. So in a case where we have many species and many phases, and we aren't exactly sure what will be the most stable species in the system, we can start studying the system by adding all of this possible species that we can find from the database. So we can do that by pressing here a new file from elements, and then we write the main components of copper smelting. So I write these elements here. Then I filter out the certain types, and I select only condensed and gases here. So now I get a list of possible species that can be formed with these elements. Then I can select all, but let's say that I don't want to select these. I only want to select the default species and not some different crystal structures, for example. So I will manually deselect some of these species by holding Control and then clicking in the list. So we click there, and so in HSC, if in the parentheses there is something else than G, L, A, or S, then usually it is somehow related to the crystal structure, or just the structure of the molecule. Okay, and then here, and then here. Okay, then I right click and import selected species. I get them here. I press the import species, and now it will ask me how I want to get them to the equilibrium calculations. I want the program automatically separate them to phases. I press OK, and that's it. Now I got pretty long lists of species here in the list. Next, I will check the phase types of each phase. So for gas, a mixture is fine. For molten sulfide and oxide phases, mixture is fine, and the same for the pure. Then I will set some initial amounts. So we got some chalcopyrite and then some pyrite here. And then I want to study how the system behaves in the smelting when I add oxygen and silica into the system. So I will define state change for X amount, and for the oxygen I will add 2 kilomoles per step, and the same for the silica. Okay, and then I need to set the temperature correctly, so I will set, let's say, 1300, and number of added steps is 100. Okay, and then let's calculate and see what are the results. And amount and equilibrium amount sounds good. Okay, so we get this kind of image. Now, because we have so many species here, it might be a good idea to filter out the system a little bit. So I check phase by phase. For the gas phase, I can see, okay, these kind of results. Then the sulfide phase, I get these results. And this is pretty interesting. I can see from here the formation of matte here. So something like this actually happens in the copper smelting, in the smelting phase. And then for the oxygen or the oxide phase, I get some silica here. Okay, and then for the pure phase. Okay, I cannot see anything there. Okay, but anyway, I can also check the phase amounts by ticking this one and then checking how the phase amounts change. So as expected, I get less or more oxide phase because I get more silica, and also the sulfide phase decreases when I add oxygen into the system. Okay, looks reasonable. And then if I want to adjust the system a little bit, for example, I know that I get firelight a little bit more, I can manually adjust the activity coefficients a little bit. So I can decrease the activity coefficients, and let's see, do I see the formation of firelight in the system now? If I select the oxide phase, now I get it here, this faint line over here. So if I take the silica out, then I can get this formation of firelight visible here in the image. Okay. So of course, again, these are calculated with the thermodynamical equilibrium and just with some main components. So these results, of course, don't necessarily represent the real life scenario, but at least you can quite easily study some preliminary behavior of the system. If you have some ideas what kind of elements are available there, and also have some idea of the system state. Okay, so that's it. So now you should be able to use all the main functions of the equilibrium calculations module, define your own systems, and set the correct calculation parameters for the system. And that's it for this tutorial. So thank you for watching.